Good morning, students. Welcome to video lecture on electromagnetic waves and transmission lines. Subject code U18EC 403. Topic work and potential. Work, it is also called energy stored in the system. Units are joules. The potential is represented by V. The units are volts. The work is represented by capital W. Both are scalar quantities. Uh, it is origin. At the origin, capital Q charge is present. Consider a point A which consists of small q with position vector R A. Now, the force at A is equal to 1 by 4 pi epsilon small q capital Q by RA square. The direction of the force is AR cap, equation 1. And the field at A, E or A is equal to 1 by 4 pi epsilon capital Q by RA square AR cap. What it means is uh, the electric field at A depends on the charge capital Q, not on small q. Uh, in simple words, we can say that F is equal to EQ. Equation 3. Consider one more point B. Its position vector is RB. Uh, due to capital Q, the electric field E present in this region, and with the presence of electric field, we are supposed to move the charge small q from point A to point B. For that, consider a differential element dl. Its position vector with respect to origin is r. Once again, listen here. Due to capital Q charge, E electric field is present in this region. With the presence of electric field, we are supposed to move the small q charge from point A to point B. For that, the differential work done in moving the charge by the length of dl, the work done in displacing the charge by length dl, uh, the work done dw is equal to minus f dot dl. Equation 4. Now here the negative sign indicates the work is done against the force. Let us continue our discussion with equation number 4 in next PPT. The differential work done in moving the charge by the length dl is minus f dot dl Now here the total work done is the integral of dw is equal to minus integral of E dot dl. The q is constant. It will come out of the integral. Now the w is equal to minus q integral E dot dl, and w by q is equal to minus integral of E dot dl. Let it be equation number 6. And here W by Q means it is the work done per unit charge, is simply the potential work done per unit charge, is simply the potential. It is represented by V. The units are volts. Once again, I repeat, it is a scalar quantity. Let us continue our discussion with equation number 6 in the next slide. The potential V is equal to W by Q is equal to minus integral of E dot dl, equation 6. The definition of potential is work done per unit charge in moving the charge from infinity to R. From infinity to R, that is from infinity to R. The general equation for electric field is 1 by 4 pi epsilon q by r square ar cap. Now let us substitute equation number 7 in 6. We get V is equal to minus from infinity to R, E is equal to 1 by 4 pi epsilon q by r square ar cap dot. The dl is along the radial direction, it is dr ar cap. The dot product ar dot ar is equal to 1. It will become minus of integral from infinity to r 1 by 4 pi epsilon q by r square dr. Once again it is equal to q by minus q by 4 pi epsilon. The integration of 1 by r square is equal to minus 1 by r. The integration limits are from infinity to r, and after rearranging we'll get the value of potential as 1 by 4 pi epsilon q by r. There is no vector quantity as potential. The electric potential is a scalar quantity. Let it be equation number 8. Now let us continue our discussion in the next PPT with this equation. The potential difference, work done per unit charge in moving the charge from point A to point B. V is equal to minus Q by 4 pi epsilon minus 1 by R in moving the charge from point A to point B, and it will become VAB. It is the potential difference between A and B represented by VAB is equal to Q by 4 pi epsilon 1 by RB minus 1 by RA. Equation number 9. Equation number 9. Once again, I will write the potential difference between the 2 points AB represented by VAB given by 1 by 4 pi epsilon 1 by RB minus 1 by RA. The potential due to n number of point charges. Consider the position of origin. Some Q1 charge present with position vector R1. One more position with position vector R. At this point, we are supposed to calculate the potential. The potential at R due to point charge is given by 1 by 4 pi epsilon Q by R minus R1. At which point you require the potential, you are supposed to write as the first position vector, then followed by the other point. Let it be equation number once again. It is 10. Due to n number of point charges, it is a position of origin. Q1 charge with position vector R1, Q2 charge with position vector R2, like that. Qn charge with Rn, and we are supposed to calculate the electric field at a point with position vector R. V of R due to n number of point charges is given as 1 by 4 pi epsilon summation k is from 1 to n qk by modulus of R minus Rk. Let it be equation number 11. Here equations 10 and 11 are useful in solving problems. You are supposed to remember these two equations. The relation between E and V, it will constitute one of the Maxwell's equations in static field. Consider a closed curve with points A and B in this direction. Based on the properties of static electric field, the potential VAB is equal to minus of VBA, and it is equal to VAB plus VBA is equal to 0. Equation 12. What it means is the potential difference between A and B and the sum potential difference between B and A is equal to 0. The basic definition of electric field is the potential is V is equal to minus integral of E dot dl. Now here VAB from point A to B plus VBA point B to point A, it is equal to 0, means equation number 12 can be written in terms of electric field as closed line integral of E dot dl is equal to 0. And by applying Stokes theorem, the closed line integral of E dot dl, the equation number 13 will become del cross E, surface integral of del cross E dot ds is equal to 0. From this we can write del cross E is equal to 0. Let it be equation number 15, and it is one of the Maxwell's equations. And this equation is valid only for static fields. Valid only for static fields, not for time varying fields. And you're supposed to remember here the key points are uh, V is equal to minus open line integral of E dot dl, and if it is closed line integral, it is not equal to V, it is equal to 0. Please make a note. V is equal to minus open line integral of E dot dl, and if it is closed line integral, then it is equal to 0, and these two equations are valid for static fields, not for time varying fields. The relation between E and V, we know the basic equation. V is equal to minus E dot dl. The electric field E is equal to Exax plus Eyay plus Ezaz, and the differential element dl is equal to dxax plus dyay plus dzaz. Now here uh, v is equal to minus integral E dot dl. By applying the partial differentiation, dv is equal to minus E dot dl. Here dv is equal to minus E dot dl. By performing the dot operation, equation number 16, let it be equation number 16, that is minus ex dx minus ey dy minus ez dz, and the partial differentiation dv is equal to dou v by dou x dx plus dou v by dou y dy plus dou v by dou z dz. It is once again the definition of dv, and from equations 16 and 17, by comparing we get the value of ex, ey and ez as shown by equation 18, and equation number 18 can be rearranged as E is equal to minus of del V. It is another type of relation between E and V. By knowing the value of potential, we can determine the electric field intensity. Let us refer to sample problem. Uh, 2-point charges Q1 and Q2 are located at position vectors R1 and R2. We are supposed to calculate the potential at another point R3. That is, you can refer to the formula. V is equal to 1 by 4 pi epsilon summation k is from 1 to n qk by modulus of r minus rk. Here you can consider this point as r. If it is r, then r minus rk. For 2-point charges, the value of k is from 1 to 2. You can substitute in the formula to get the value of potential. Refer to sample problem 2. The problem is given in spherical coordinate system. No need to worry about the coordinate system. You can calculate the potential difference between AB, that is work done per unit charge, multiplied by Q, VB minus VA. The value of V is given. Substitute the points A and B to get the potentials at A and B, and substitute in the equation to get the value of work done or energy stored in the system. It is in terms of joules. Sample problem 3. It is based on the relation E is equal to minus of del V. You are supposed to determine the electric field intensity based on potential, and once again you need to substitute in D is equal to epsilon E to get the value of electric flux density. It is in terms of coulomb per meter square. Continue the solution. Practice problem 1. In most of the cases, if the medium is not defined, then you can consider the value of epsilon as epsilon naught. It is equal to 8.854 into 10 power minus 12 farad per meter, or 1 by 4 pi epsilon naught. In general, it is considered as 9 into 10 power 9. Refer to practice problem 2. Thank you. We will meet with the next lecture.